In this lesson, we continue to discuss the physical properties of organic molecules by considering melting points, polarity, solubility, and density. Recall in the last lesson that we talked about intermolecular forces in general and how they apply to boiling points. So for melting points, the trends tend to be similar to the boiling point trends in that bigger molecules with larger intermolecular attractive forces tend to have higher melting points. But there's one key addition to the trends for melting points, and that is the concept of crystal packing. Okay, and the general principle is that molecules that can form well-ordered crystals, or highly symmetric molecules, as we shall see, have higher melting points. So let's look at some examples. Benzene, a 6-carbon hydrocarbon, has a melting point of positive 6 degrees Celsius. That should strike you as a little high for molecules with only 6 carbons. In fact, I don't think I can name another 6-carbon molecule with such a high melting point. If we look at a structure that is similar to benzene, that of toluene, in which we have 7 carbons and 1 methyl group coming off of the benzene ring, you would expect that if this is a larger molecule, the melting point would be higher, right? Well, truth is experiment, and if you measure the melting point of this molecule, it's negative 93 degrees. Okay, almost 100 degrees lower than the melting point of benzene. What's going on here? Well, I got another example for you. Hexane, also a 6-carbon molecule, has a melting point of negative 95 degrees. Okay, so that should tell you that benzene is the anomaly, right? For a 6-carbon molecule, we would expect it to have a melting point fairly low, for it to be a liquid well below 0 degrees. But 2-methylpentane, an isomer of hexane that is branched instead of linear, has a melting point of negative 154 degrees. So it is much, much easier to melt solid 2-methylpentane than it would be to melt solid hexane. So the phenomenon is the same in both of these cases, and it is that of crystal packing. So drawn here would be how a number of benzene molecules can come together to form a crystal. Benzene is basically comprised of hexagonal-shaped molecules, and hexagons are a geometric shape that is capable of tessellating a plane, which means you can fill all the white space on a piece of paper with hexagons, or if you're an organic chemist, with benzene molecules. However, if we try toluene molecules, you've got that methyl group there sticking out and taking up space. So you know, I attempted to draw some toluene molecules, and I probably did not even leave as much space as I needed to for the 3 hydrogens on that methyl group. So in a space larger than where I could fit 7 benzene molecules, I can't even fit 5 toluene molecules in the crystal. And that is assuming that they are all lined up the same way and are as what we call well-ordered as possible. And that's not necessarily always going to be a true assumption. Okay, so because benzene molecules can pack more efficiently than toluene molecules, the melting point of benzene is much higher than the melting point of toluene. Similarly for hexane, because it is a very regularly shaped molecule and there's no methyl group sticking out off of one side of it, if you get cold enough, in other words, you have to get a lot colder than you do for benzene, the hexane molecules can stack one on top of each other and you can get them to form a solid structure. Whereas the 2-methylpentanes have that methyl group sticking up there such that it's really, really hard to get them to pack into a crystal. Thus, the melting point is very low. Polarity and solubility are 2 very interrelated concepts, And they are important because of the general principle that like dissolves like. In other words, polar molecules will tend to dissolve in polar solvents, and nonpolar molecules will tend to dissolve in nonpolar solvents. Most organic compounds are less polar than water and therefore are not soluble in water. So as a result, in order to be a well-rounded student of organic chemistry, you have to have some familiarity with a number of molecules that are used as common organic solvents. Okay, these are molecules that tend to be small, tend to be relatively cheap compared to other organic molecules, and in most cases tend to be volatile enough, in other words, have low enough boiling points that they can be removed by evaporation when you are done using them. I am going to personally classify organic solvents into three categories: the nonpolar, the moderately polar, and the polar. These are my classifications. The polar ones have a well-defined definition. Those are going to be molecules that are miscible with water. You should recall that miscible means soluble in all proportions. What that means is I could take 10% organic molecule, 90% water, and it will all dissolve. 20% organic, 80% water, it's all dissolves. It's all homogeneous. 50% organic, 50% water, it will all be homogeneous. It doesn't matter what proportions I use, we will always have a solution. The moderately polar molecules are molecules that have some small solubility in water. You can usually get a few drops into water before you will exceed the solubility. And the nonpolar molecules are molecules that, as far as I'm concerned, have essentially zero solubility in water. Okay, so I'm going to give you 11 examples of good solvents to know. The nonpolar ones, we have hexane, benzene, diethyl ether, and chloroform. For the moderately polar ones, we have tetrahydrofuran, which is sometimes shortened to THF. And I like to say that tetrahydrofuran looks kind of like ether with its arms tied around its back. But the fact that it has its arms tied around its back means that it's going to have a permanent dipole pointing up towards that oxygen now, isn't it? Dichloromethane has a permanent dipole pointing towards the two chlorines. And then ethyl acetate is an ester. It has both a carbonyl group, a CO double bond, as well as another oxygen in the chain of the molecule. So all of these provide for permanent dipoles in these molecules and make them moderately polar. And the polar molecules that you should be aware of are acetone, ethanol, methanol, and acetonitrile. Water solubility for molecules containing a similar functional group will also vary as a function of molecular size. So indicated on this slide is some data for alcohols. And for each alcohol, I'm giving their water solubility in units of grams per 100 mils. So as we saw on the last slide, methanol and ethanol are both miscible with water. Propanol is also miscible with water. But once you get to butanol, it's no longer miscible with water. You can still get quite a bit dissolved. You can get 8.3 grams of butanol into 100 milliliters of water. But once you try to dissolve more than 8.3 grams in 100 mils, it's going to start to separate out because you've exceeded the solubility. For pentanol, the solubility is 2.4 grams per 100 mils. For hexanol, it's 0.6 grams. For heptanol, it's 0.2, and for octanol, it's about 0.05. For these last three solvents, I've given you a better indication that may be more useful than amounts that are less than a gram. 0.6 grams is about 60 drops, 0.2 grams is about 20 drops, and 0.05 grams is about 5 drops. So that's all you can get of octanol into water before it starts to separate out. And in fact, in medicinal chemistry, one of the parameters about drugs as to how water soluble they are is a measure of what's called their octanol water partition coefficient. would they rather dissolve in octanol or water? Because that is the smallest alcohol that really has negligible solubility in water. Okay, the last topic in this lesson is density, because for molecules that are not water soluble, those that are less dense than water will float to the top, and those that are denser than water will sink to the bottom. Okay, so let's look at some data. Water has a density of exactly 1.00 grams per mil. So molecules such as hydrocarbons have densities between 0.6 and 0.7 grams per mil. They are less dense than water, so they're going to float on water. This is commonly seen because oil floats on top of water, and oil is basically made of hydrocarbons. Similarly, alcohols, ethers, and esters do not have quite as low of a density as hydrocarbons do, but their densities are still less than that of water, and if you have a mixture of the two compounds, the organic layer will be on top and the water layer will be on the bottom. Okay, so most organic compounds are less dense than water. I say most because the key exception are the halogenated molecules. So dichloromethane has a density of 1.325 and chloroform has a density of 1.492. Okay, how do you think about this? You could just remember these numbers, but I don't like organic chemistry to be about memorizing numbers. I like organic chemistry to be about understanding the underlying concepts behind these numbers. Okay, so water is mostly oxygen. So we'll kind of call that the default. It's got a density of 1. Carbon, if you recall your periodic trends, is to the left of oxygen on the periodic table. So that means it's got a larger atomic radius than oxygen does. And it is also lighter than oxygen. A carbon atom has a mass of 12, whereas an oxygen atom has a mass of 16. So carbon, therefore, is less dense than oxygen is. It's got less mass in a greater volume. So organic compounds, which are mostly made of carbon, are going to be less dense than water. Chlorine, on the other hand, has a relatively small atomic radius because it's over on the right-hand side of the periodic table. And chlorine has a mass of either 35 or 37, depending on which isotope you are referring to. So it packs a lot of mass into a relatively small space. So that's why chlorinated compounds are denser than water and, of course, denser than most other organic molecules. And as you can see from the data, the more chlorines you have in your structure versus the same number of carbons, the more dense the molecule is going to be.